All right. So before I get back to material, I apologize for blasting you with email after email. Whatever. About Orion, I'm gradually learning how to use it myself. I still have a couple questions to ask the technical people at the publishers to understand. About Orion, this first chapter, I'm going to be way lenient on everything, every aspect of it, partly because we're learning how to use this stupid thing. As I said in my emails, this diagnostic that precedes the Orion practice was a shockaroo to me. It's all quantitative questions that are really, they're actually fairly difficult. They require me to think, okay? And I don't even think I got all of them right, because I was trying to get through them. But in any case, you're welcome to just kill that diagnostic by pressing the little red X that gets rid of it and go right into Orion. The Orion for Chapter 1 also has some quantitative questions in it. Not so many, and they're maybe okay. The point of using the Orion, it's new to me, it's new to you. The website just simply a completely different one than I've ever used before, I've been involved with before. The purpose of it is to help you understand and learn the material. I do not mean to be increasing the pressure on your lives with it. And so I'm going to work on figuring out how to use it in a way that's as helpful and as least harmful as possible. So that's going to take a little bit of work on my part. I assigned officially 20 questions, meaning that once you have completed 20 questions in the Orion section, and you can skip them, but they don't count, of course. Once you've completed 20, then you're eligible for credit. And if at that point you have 60% or more right, you're eligible for full credit. If you're below 60%, you can keep taking questions to try to boost your percentage up higher. There seem to be more than one. You can check some important things. To see whether you got one right or not, take a look at your little bar graph that goes perking along as you answer questions. A green bar indicates that you got it right. A red bar indicates that you got it wrong. So you can see it's helpful to know whether you got it right or not, right? If you want to see where you stand, there's a link you can click that shows you your progress and will report to you. I think it reports the number of questions you've asked and or the fraction you're getting correct. I'm a little confused about it myself, and I need to get expert help, and so I will check on that. In any case, muck around with the Orion stuff. I'm going to just be wildly lenient on this Chapter 1. We'll get it figured out by Chapter 2, I hope. Anything else that I should think about or talk about with respect to the website? One other thing. A week from today, the first real, what I call a problem set, you may call it homework, it gets different names in different places, is due. And that is really 20 questions for the money, right? It's actually scored. You get them right or you get them wrong, you get one shot at them. That's the way it is. And don't be late on that, because that really has a deadline. The Orion stuff, I think I've resolved to make the deadline after the class is done at the end of the semester. So I now have it scheduled for after the final. In other words, do it when you're ready for it. Yeah. The Orion, I've said it so the Orion is due at the end of the semester. Don't put it off. Don't put it off beyond the point at which you're ready for it, because it'll just linger and you'll be there during the end of the final exam trying to finish, right? It's not very good. There is an issue about taking it too early. If you go in there before we've ever covered 90% of the material, and you haven't read ahead yourself, it's going to be like, what is this? So many of you have already gone after that Orion stuff, and you've encountered things that I haven't talked about in class yet. And I know there was some confusion about when it was due and all that. As I say now, it's due way off in the future. Don't worry about due dates. Just do it eventually. But I'm going to talk today, I'll get into ramps. Hopefully I'll get into energy, which is one of the features of ramps, that the biggest concepts that shows up in it. And then those energy questions that are in the Orion for Chapter 1 become appropriate and relevant and useful. 2 days ago, they weren't very useful. Other questions? All right. Just in terms of my own class philosophy, basically, is that the concepts are so much more important than the formulas and calculations. And the calculations, they're fine for physicists. They're potentially fine for art majors and history majors and stuff. However, they're potentially a distraction from the concepts. I care that you learn the concepts. That's already enough. It will be a challenge. Some of you will ace get the concepts completely, but others of you will struggle with some of these issues for a very long time, and that's fine. It's normal. Things like, what's the difference between velocity and acceleration? And the fact that forces cause accelerations, they don't cause velocities. That observation, that's not easy. Some good fraction of you are dealing with that now, and it will take a while for it to make sense. Okay, so getting that straight matters much more than being able to calculate a mass of 7 kilogram mass with experiencing a 3 kilogram force. 3 kilogram force, 3 Newton force. Those questions are not only boring, they are easy to write, they are boring, and they don't serve much purpose, in my view. All right. Back to falling balls. So I'll finish up with falling balls, and then I'm going to go on and talk about ramps. And the big picture issues with falling balls are that when any object is experiencing only its weight, nothing else, it is a falling object, and it is accelerating downward at the acceleration due to gravity, which happens to be here at the surface of the Earth, about 9.8 meters per second squared. Incidentally, for those of you who are unfamiliar with metric stuff, a meter is about like this. Okay? There have been big pushes in the U.S. to try to switch us all over to metric. They have been relatively unsuccessful. It's just so hard to do it. Things like all the tools, all the gadgets are built locally. They're all built in these English units. My laboratory is sort of a 50-50 mix of English stuff and metric stuff. And I'll pull out a bolt that's just been sitting around. It's like, which is it? Is it English or is it metric? You put it in the wrong nut and it doesn't, binds up. It's terrible. So, 1 meter. An acceleration of 9.8 meters per second squared means that a falling object develops about 9.8 meters per second of downward velocity if you drop it from rest in the first second. So that's that. And this downward acceleration occurs regardless of what the velocity of the ball is. The ball's velocity can be heading downward at some value. It can be heading upward at some value. It can even be right at the top. So that brings me to this question. I mean, I've got very relatively little to talk further about falling balls, but suppose we're not talking about a ball now, but you on the springboard at the AFC. You're bouncing up and down, and you jump upward, and let's assume you jump exactly straight up, and I realize this leaves you with the opportunity to hit the board on the way down, but it's my story. So up you go, straight up, and right at the top of your travels, at that instant, I want to know your velocity and your acceleration according to these 4 possible choices. You okay with the question? Questions about the question? So at that moment of peak height, how about A says your velocity is changing, but your acceleration is constant. How many think that's the case? Okay. B, the choice is your velocity is constant and your acceleration is constant. Okay. C is that your velocity is constant, but your acceleration is changing. Okay. And D is your velocity is changing and your acceleration is changing. Okay. The majority of those who voted, which is a small fraction of the class, this was like a primary in an uncontested race, was C. So I would say 10% of you are going for C, 5% each for A and B, and nobody for D. pretty much nobody for D. The correct answer is A. Now, why is that? Your velocity is changing, but your acceleration is constant. At that peak height, as in the entire trip of the ball up and down after it's not, when it's not in my hand, the ball is falling. Even at the top, it's still falling. It's experiencing only one force, its weight. And therefore, it's accelerating downward at 9.8 meters per second. Constant acceleration downward. You okay with that part so far? It may not feel good, but at least you ought to, if you heard my words, it's right. There's nothing special happened at that peak height that turned off the acceleration or changed it. It's just experiencing its weight. It's falling. And as for its velocity, the fact that the ball is accelerating throughout its entire trip, and in general, and at the top in particular, the fact that the ball is accelerating means its velocity is changing with time. That's what an acceleration is. So if you think about that moment, let's visualize that moment at the top. A moment before that, just roll back the video a little bit. The ball was heading upward. So its velocity a little earlier was upward. Let's go a little forward, past the point of peak height to the moment after. Now the ball's heading downward. So it went smoothly from heading upward, from a velocity that was upward, through zero to a velocity that was downward. So at the moment of peak height, that was the moment when it finally stopped heading upward and is about to, but hasn't yet, started heading downward. So it's the moment of zero velocity. You okay with that being the moment of zero velocity? But throughout this process, the ball continued to accelerate downward. In years past, it's been helpful for me to just draw a graph of, let's see, what's the right graph? Yeesh. Oh. This is time. I don't usually use graphs and stuff. This is a conceptual course, but I'll do it anyway. And this is velocity, where being on this side of that horizontal axis means upward, and this is downward. As time goes by, the ball, when it left my hand, was heading upward fast. So it's up here. The velocity is a high, positive, a number up above the horizontal axis. That's okay? It's going up. And it's accelerating steadily downward, which means that it's losing velocity. Perfect straight line, and it goes right through zero. And right there at that point, when the velocity passes through zero, it went from being heading upward to heading downward. It's right in between. No velocity. But that doesn't mean that it's not changing. The velocity is still changing with time. It just cruises right through the zero moment. Is that helpful? Yeah, Liz. Before it reaches its peak, is the acceleration changing or constant? It's constant. It's a falling ball. So while it's in my hand, things are complicated because I'm pushing too. But once it leaves my hand, and neglecting any air effects, the only force acting on it is its weight. And that's not changing. And its mass isn't changing. And remember, its acceleration is simply the force acting on it divided by its mass, both of which in this case are constant. So it's 9.8 meters per second squared the whole time. Yeah. So for all falling items, the acceleration is constant and the same. That is true. That's why I can take a whole handful of stuff and throw it, or drop it together. Throwing it, often you give one a little bit more of an initial velocity than others. But if you drop a whole handful of things, they all accelerate downward at 9.8 meters per second, which means they all develop this downward velocity at the same rate. They all go together. And physicists have been looking, in effect, for 50 years, maybe 100 years, for an exception to that rule, because it would be a huge thing, and it's never been observed. Everything falls together. Yeah? So what's the difference between acceleration and speed? And this is one of the great challenges of this early part of the class, is really distinguishing those. Speed is a piece of velocity. That is, it's a portion of the concept of velocity. Velocity is both speed and the direction in which the speed is acting. So it's a little more, there's more information in velocity than in speed. So what you're sort of asking is the difference between this, its acceleration and its velocity a little bit. I mean, that's what you're looking for, is how are those related, I guess. I've lost the exact form of your question. So ask it again. Yes. Okay. So now the question is, as the ball is falling, it acquires more downward speed with passing time, which I can embellish by saying its velocity is downward and increasing with time. So the velocity is getting bigger and bigger in the downward direction. Is that okay so far? How can that be the case, and yet its acceleration is somehow different and, in fact, constant? It's because acceleration isn't velocity. Acceleration is how the velocity is changing with time. And if you watch a falling ball and you go there and you measure with a ruler and a stopwatch how it's descending, you'll discover that the method in its madness of descending is that with every passing second, its velocity increases in the downward direction by a very specific amount. Every time a second passes, the velocity increases by 9.8 meters per second. And every fraction of a second, it increases by a corresponding fraction of 9.8 meters per second. So its speed is increasing down. It's all downward, steadily with time, always the same increment per second. And what that means is it is accelerating steadily. That's what acceleration means. It is how velocity is changing with time. So the fact that the ball is a falling object is accelerating at a constant rate means its speed in the downward direction is increasing steadily at that acceleration rate. Is that okay? I hope this is helpful to people. This is one of the central issues. It's sort of getting it clear in your mind the difference between acceleration and velocity, because it's not obvious. When I first started teaching this class 25 years ago, give or take, I assumed it was obvious. I'd been immersed in it long enough that I've forgotten that it was a puzzlement to me. And I've since, I pretty quickly realized, oh my gosh, I'd forgotten how hard it is to distinguish these things. And it is. Yeah. So the question is whether, on a graph like this, is it safe to say that as the velocity crosses zero, is it turning around? And the answer in this case is yes. A graph like this only works when you've got motion along one direction. What I think of as a railroad track. You're going in somewhere along a straight line. And if you're not going in a straight line, if you're going, motion like this, you can't describe it on a simple graph. It's got many dimensions to it. You can't do this. You can do this in the case of a falling object that's going straight up and straight down. And then the velocities above the zero correspond to upward velocities, and the ones downward correspond to downward velocities. And as you go through the zero, it goes from heading upward to heading down. That's the turning around. We can do the same thing if I lived on this railroad track right here, and I went from going this way, I slowed down, remember my acceleration opposite my velocity, and I turn around. Same thing happened here. Right at this point, my velocity went momentarily to zero, and I kept accelerating, and I turned around. So my velocity swept through zero. In that case, the top part of velocity might be toward your right, and the bottom part of velocity might be toward your left. It's just a shorthand way of writing it, describing it in the simplified world where there's only one dimension to worry about. Okay, other questions? I've got one last thing to talk about with respect, I'm going to blast through, with respect to falling objects. Weight affects objects vertically only. In fact, it basically defines vertical. Gravity defines vertical for us. You find the vertical by hanging a plumb bob at the end of a string and waiting for it to settle, and you know that line now is dead vertical by definition. And it's a gravity measurement. So What if a ball isn't going straight up and straight down, but rather at an angle? How does that make, does that mess everything up? And the answer is no. What happens then is the object's weight affects only its vertical component of motion. The word component is what it is. It's a probably mathematical term as much as a physical term. So the ball, when it's going in some cockeyed direction, it has components along various dimensional axes. In this case, the vertical motion is a falling motion, but the horizontal motion, component, Samsung S7, whoa, okay. Samsung S7. The horizontal component of the motion is that of coasting. And I can show you so this arc that I've got up here, that arc, which happens to be mathematically a parabola, which is kind of interesting, but not important, it's coasting steadily horizontally. At the same time, it's rising to a peak momentarily, motionless vertically, and then it descends faster and faster. Both motions are occurring at once. The coasting motion horizontally, the rise and fall horizontally. Vertically. Okay? Any questions so far? Having said that, yeah, some of you came to my office hours this morning and I went looking for a video. So here's the video. And, okay, I'm going to dim the lights so you can see better. This is the AFC. Hopefully the gobbledygook will clear up in a second. And I was filming these three guys. He was in the class, the other three guys, and they're shooting hoops from way outside the key. I mean, they were hitting the basket almost every time. And what I want to show you, and I'll just play it. So here he goes. He's going to shoot it. There he goes, right through. And what I then did was I mapped out the shot. So there, can I get rid of these over these guys 1 second here? There. Can you see his shot, the arc? All right? And now I'm going to start putting graphics on that. So there's his amazing shot, one of a zillion. And here's the graphics on it. And of course, this is the day I didn't bring my laser pointer. I don't know what I did with it. Do I have it? Oh, I have it. Yay. Okay. So these are evenly spaced horizontal lines. And these evenly spaced vertical lines. And the horizontal lines get closer and closer and closer and closer. So vertically, the ball is going, it's rising fast at first, slower, 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 till not at all, and then faster, 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 faster. So it has risen vertically to a peak and then descended faster and faster. At the same time, it made steady progress toward the basket the whole way. Any questions about what I've done graphically, what that means? I hope it's reasonably followable. That here you are seeing in real life a shot at a basket that has that arc. And the arc is simply showing you a vertical rise and fall of a falling object at the same time as a horizontal coasting of a object. All right? That then covers everything I think I want to say about falling balls. Any questions about falling ball stuff? Just falling in general, the motions of falling. Okay. That brings us then to ramps. So, my introductory question with respect to ramps is this. Can a ball ever push downward on a horizontal table with a force that's greater than the ball's weight? So, for example, can this bowling ball, which weighs 16 pounds, ever exert a downward force on the table that's larger than 16 pounds? You okay with the question? How many think, yes, it's possible for the ball to push harder than 16 pounds? Okay, how about no? Not, okay, so significant majority is going for no. It can't push harder. And we'll come back to that one shortly. If I get close to the end of the hour and I haven't made it, remind me and I'll jump ahead. All right, so remember that question. Some observations about ramps, that it's difficult to lift a heavy wagon straight up. So for example, here's my little toy wagon. I can turn the spots on. Not those guys. Yeah. Okay, this is difficult, okay? However, if I have a ramp and I'm allowed to pull it along the ramp, it's easy, woo, okay? So ramps are giving you some sort of advantage, making it easier to lift heavy objects. They seem to come at a cost. That is, going along the ramp, going straight up is sort of a quick and expedient way of getting it up there. Going along a ramp, you got to travel a long distance to get it up there, but you're getting it. The good news is you don't have to push very hard. The bad news is you have to go a long distance. Is there a relationship with those? Yeah, the answer is yes. What else is in here? The steeper the ramp, of course, the harder you have to push. You've all had that experience. The shallow ramps are easy but very long. Steep ramps are short, but you have to push hard. Okay. So I'll pursue these 5 questions. You'll see them come by individually. But so the first one then is why doesn't a wagon simply fall through a sidewalk? So let me reduce my ramp to a sidewalk, put the wagon on there, have the kid down the block who eats too much pizza sitting in there, and who can eat too much pizza? There is no such thing as too much pizza. Okay. So why doesn't the wagon fall through the sidewalk? And the answer is that the sidewalk pushes up on the wagon. What I'm doing then is I'm introducing the second type of force for the semester. The first type of force we encountered was weight, which is the force due to gravity on an object. This is a new one. I call it a support force. It's often called, other people would call it either a contact force or a normal force. It's the force that appears when 2 objects touch. And it comes out about just from the familiar idea that two things can't occupy the same space at the same time. They do push apart. And finally it has to do with the atoms and molecules and how they work in there. But it is the case that if you try to shove the wagon's wheels into the sidewalk, those 2 objects push on each other. The sidewalk pushes up on the wagon's wheels. The wagon's wheels push down on the sidewalk. These, what I call support forces, they always act perpendicular to the surfaces. Perpendicular is the or orthogonal. These are the fancy words for at right angles in every respect. So if a surface, to make sure this is clear to you, this surface, this sidewalk is horizontal, normal forces or support forces from this sidewalk are perpendicular to a horizontal surface. That's a vertical line. A vertical line is the perpendicular to a horizontal surface. If the surface is tilted, the perpendicular line to the surface is no longer vertical. It's up at some cockeyed angle. You okay with perpendicular direction? So support forces are always perpendicular to the surfaces that are touching. In this case, the wheels are pushing, the wheels, although they're curved, the part of the wheel that touches the sidewalk happens to be that moment when it's horizontal at the bottom, and that's pushing straight down on the sidewalk. The sidewalk, being uniformly horizontal, is always pushing straight up on the wheel. All right? You might wonder, okay, well, what about yeah? If the wagon were experiencing only one force, namely its weight, what would it do? It would accelerate downward at the full acceleration due to gravity. It would go right through the sidewalk. So the observation is, it's motionless, and it's still motionless. We have to look twice, right? Because we have to look at its velocity. Its velocity is zero. Yeah, its velocity is 0 from 2 glances. In fact, we do a third glance, we realize not only is its velocity 0, but it's staying 0. Evidently, it's not accelerating. And an object that is not accelerating, acceleration 0, is an inertial object, experiencing 0 net force. So we know the force on this is 0 by the evidence is. Physics has a lot in common. I had another discussion this morning with law. That when you build a case, which we all do in papers, scientific publications, you're building cases for your conclusions. And here's the case. It's not accelerating. The net force on it must be 0. We know it has downward weight. So there must be a second force acting on it that perfectly cancels its weight. Where's that from? It's the sidewalk pushing up. And we know how hard the sidewalk's pushing up. It's pushing up with a force exactly equal to the weight of the wagon. Is that okay? Well, that upward force on the wagon, it turns out, doesn't have to be exactly equal to the wagon. It is in this case, but somehow the sidewalk has sort of figured out how hard to push. The sidewalk doesn't necessarily know about gravity and the wagon being pulled down by the earth. It's just trying to keep that stupid wagon from drilling holes in it. So it's pushing up. And how does it figure out how hard to push? Well, it figures out by a negotiation. When I first put the wagon down, and you hear various bumps and jiggles, that's actually the wagon and the sidewalk negotiating. There's a bouncing process that's occurring during which time there are moments when the wagon pushes too hard on the sidewalk and the sidewalk pushes too hard back on the wagon, and sometimes the wagon pushes too light, and it's accelerating during those periods, but eventually it settles down at just the right point where it's perfectly supported. If I replace the sidewalk, and I should have one of these, with a trampoline, if you put a wagon down on a trampoline, it'll bounce for a while, right? You can visualize that in your mind's eye, and then eventually settle. And there's really no big difference between a trampoline and my sidewalk, except that the sidewalk, being very stiff, has that bouncing motion very small. It is still there. You can't avoid it. These are the ideas of immovable objects and irresistible forces and stuff. There are no perfectly rigid objects. If the floor were diamond, well, we would end the lecture and I would go sell it. If the floor were diamond, however, and I came and I jumped on it, I would dent the diamond, just not very much. So during the landing process, there is a negotiation going on. Actually, I can show you the landing process. I don't have a trampoline, but I do have a springy scale here. And this device will tell us how hard it's pushing upward on something. If, for example, I put this weight on it, it will tell us that it is pushing up with 49 newtons of force, which is good because this is a 5 kilogram object. 5 kilograms, and every kilogram weighs 9.8 newtons. 5 times 9.8 is 49. Yes, it's pushing up with a force upward that's exactly equal in amount to the object's weight. As a result, the object is experiencing 0 net force. It's not accelerating. It's inertial. All right? But during the landing process, watch what happens. All over the place. The scale is correctly telling you how hard it's pushing. And it's all over the map. Because why? Because when the object first comes along, the scale isn't pushing on it at all. It's reading 0. As a consequence, this block is accelerating downward, the full acceleration of gravity. If I let go of it, it's going to fall, right? And then it will touch. It'll touch just its tippy toe, just touching a little bit. And at that first little touch, their support forces appear. These things begin to push each other apart. The block pushes down on the scale pushes up on the block, and now we're at 15 newtons. And then, so the block will still be accelerating downward, just not as fast. It's partly supported. And then we'll come to 49 newtons, right there. And now the block is perfectly supported. However, the block arrived there moving downward. and it hasn't come to a complete rest yet. It will overshoot. It will go right past that special point at which it's perfectly supported and dent too deeply into the scale. So you're following the I can't do two things at once. So hopefully you can picture this idea that as something lands on a springy surface, this can be you on a trampoline. This can be your backpack thrown on your bed. Any of those things. It's not supported while it's not touching. Once it begins to touch, it begins to get a little support as it dents that surface it's landing on. And the support gets stronger and stronger as it dents deeper and deeper. And it continues to accelerate downward up until the point at which it's finally, at last, fully supported. Prior to that, it's still got a net downward force. So it's still accelerating downward. Still speeding up in the downward direction, even though it's touching. Is that okay so far? That it's still speeding up. When you throw your backpack onto the bed, it doesn't stop accelerating downward when it first touches. It doesn't stop accelerating downward when it dents a little bit. It takes a pretty good dent before it's supported and stops accelerating downward. But it reaches that moment of not accelerating downward while it is moving downward. So its acceleration drops to 0 when it's perfectly supported, but that doesn't mean its velocity is 0. It's still moving downward, and it overshoots. It goes extra deep into the bed. And it's during that extra deep dent into the bed that finally it's pushed up so hard by the dented bed with a support force that it's accelerating upward now. And it slows to a stop, is momentarily motionless, and then it actually begins to move upward. That's the full bouncing process. It actually continues past that. But that's what you see here. When I drop this guy, I'm not going to drop it very far, it actually overshoots 49 newtons, woo, and then bounces. Hopefully you can see it bouncing up and down. That's it negotiating, going, if it's dented too far, it's accelerating upward. If it's dented too little, it's accelerating downward. It's trying to settle. It's got beautiful feedback where eventually it comes in and settles just right. Long story. Hopefully it's followable. Questions about it? Things that you didn't understand what I just said? Yeah? What happens when you throw something and it shatters? Of course, it doesn't shatter in midair, right? It shatters when it lands on something. When it lands on something, if you drop it on something, and this is great, okay, when it lands on something, it begins to, first it touches a little bit, and it's slightly supported. It is, however, still accelerating downward, because it's still got a net force down. You all can follow that idea? It begins to dent further and further and further. It gets to the equilibrium point. Equilibrium, I use the word equilibrium. Equilibrium is the moment when you hit, is the location at which perfect support appears, and the object is experiencing 0 net force. That's called equilibrium. Okay? So it reaches equilibrium, and then it goes beyond equilibrium because it overshoots. And it begins to push extra hard on the table, and the table pushes extra hard on it. The question is, can the table and can the it take that force? And maybe not. And if it can't, if you throw the Ming vase onto the diamond table that someone gave you, it's going to be bad for the vase, because the vase will begin to dent. Is it a vase or is it a vase, or am I being pretentious saying one or the other? I don't know. As they touch, they begin to dent. The table's denting, the vase is denting. Can they take it? And they can't always take it. So, is that okay? So if I drop this bowling ball on the table from this height, they negotiated, and it settled. If I go to the catwalk up there and drop it on the table, we don't count on it negotiating successfully, right? So there's a limit. Now, when they did this whole story, think back to, where's the question going to come up? No, I want to do that. I want this question. I'm just going to go back to it. Remember this question? There we are. Can a ball ever push downward on a horizontal table with a force greater than the ball's weight? The majority of you, I'll remind you, said no. Why don't you discuss it with each other for a minute? Talk to your neighbors and come up with another answer for this. Oh, well, come up with an answer for this. No. Okay, so we're now a minute in. Hopefully you all have an opinion. How many think, so the question again is, can the ball ever push downward on a horizontal table with a force greater than the ball's weight? How many think yes? How many think no? It's nearly unanimous. Yes. The answer is yes. Give me a circumstance in which the ball will push downward on the table with a force greater than its weight. What can I do when I drop it? Is it, well, right? Well, I'll hope he said that. Right. If I do this, the net force on it right now is 0. Evidently, the table is pushing up on it with a force equal to its weight. It, incidentally, is pushing back equally hard, which is an interesting observation, one I have to flesh out properly. They're pushing on each other. But if I drop it, during that moment of impact, it's pushing like crazy on the table. And the table is pushing like crazy on it. Why? They're in danger of occupying the same space at the same time, and because they're approaching each other, this is going to happen quickly. How do they solve it? They push each other apart so hard that they accelerate each other away from each other. They bring each other to a stop and push each other finally apart. Yeah? What net force is? Net force is the overall force acting on an object. So if there's only a single force, as in a falling object, the net force is the weight of the object. But if there are several forces acting on it, you have to add them. And you have to add them taking into account the directions of the individual forces. So in this case, the ball's weight is downward, but it evidently has a second force acting on it, or at least one other force. How do we know it's got another force acting on it? Is it not moving, or is there something more than not moving? It's not accelerating. It can be not moving for an instant and yet have a net force on it in the process of coming to a stop. A ball, when I throw it straight up, there is that moment when it's not moving, but it's still accelerating, okay? The net force is not 0. We know the net force on this is 0 because it's not accelerating. But if it is accelerating, then evidently it's got a net force on it. And that means that its weight downward and the force up on it from the table don't cancel. And that's what's happening at this impact. At that moment of impact, the weight is small, it's the downward weight, but the upward force on the ball is way larger, much stronger, and the ball is accelerating upward as a result. A name for that kind of force, where two objects collide and they push on each other ferociously, we often call them impact forces, and they show up all over the place. For example, one great example is a hammer and a nail. How do you get a nail to go into a piece of wood? You have to push it in. Well, if you try to push it with your thumb, it's going to hurt, and you're not going to make much progress. So what do? You get something moving, a hammer, and you have it hit the nail. And there's now, during that brief moment of impact, there's this tremendous conversation going on. Okay, I anthropomorphize everything. So the nail and the hammer are talking to each other. Oh my gosh, you're gonna come and occupy my space. This is bad. Hammers, get out of my way. I'm moving. I'm going to keep going. Okay, nail, no. I forbid it. I push back on you like crazy. I bring you to a stop. How How hard were you willing to push on me? Way super duper duper hard. Okay, I push like crazy. And now, hammer pushes back like crazy because they have to push equal numbers. The hammer's incredible push on the nail pushes the nail into the wood. So there's this conversation between the wood and the nail going, no, don't drill holes in me. Sorry, I'm really being pushed hard. In you go. Okay? Still, I mean, okay, fun and games aside. This is how a hammer works. You can pound a nail, and it has nothing to do with gravity. It's the impact between these two objects and the tremendous forces they exert on each other trying to keep each other from occupying the same space. And it works. You can nail into the ceiling, right? You can pounding a nail, you can pound into the ceiling. It doesn't have anything to do with gravity. I mean, just trivial. Gravity is such a trivial component of this. It's that collision that matters. And regarding the question about why do things break sometimes, water balloon, okay? So the water balloon evidently can tolerate a force on its surface that is equal in amount to its weight. Right now it weighs, I don't know, a pound, which is the unit of force. And the table is pushing up on it with a force equal to a pound, and everybody's happy. But if something exerts a force of 100 pounds or 1,000 pounds on that water balloon, it's going to be toast. How can I get something to exert a force of 1,000 pounds on that water balloon? You tell me. Drop it. Make it try to occupy the same space as the table at the same time. The two objects will push apart on each other like crazy, and this is bound to be bad for the water balloon. Ha! Normally balloons go bad with age. They burst more easily. These water balloons go the other direction. Yes! Physics is saved. So what broke the balloon was a tremendous upward push from the table on the balloon, more than the balloon could tolerate. This does bring me to an issue. Okay, I can only complete so much stuff in so much time. Yeah? Okay, if the weight of the balloon is not changing as the balloon hits, why does the table have to compensate? It is true, the balloon's weight never changed. It's still the same, it just happens to be dispersed. The weight's still there. But during the impact, it wasn't a weight, the issue wasn't the balloon's weight so much, although it did affect the balloon a little. It tends to pull downward on the balloon. The most important forces and issues were the balloon had a downward velocity, and it has mass. So it's got inertia in the downward direction. It's got a tendency to keep going downward. To stop that, to bring it to rest, the table has to push up on it and cause it to accelerate upward. In pushing up, to a tiny extent, the table was trying to support the weight of the balloon. But to a much greater extent, most of the table's upward push wasn't compensating for the balloon's weight. It was compensating for the balloon's downward velocity and trying to slow the balloon to a stop. So the balloon, by virtue of its mass, keeps going, and the table has to stop it quickly. And it does that by exerting a tremendous upward force on the balloon. So the balloon was beginning to lose its downward velocity in hundredths of a second. It was going from heading downward at 5 miles an hour, to pick another unit of speed, to 0. It was going from 5 to 0 in a hundredth of a second. That's a big change in velocity. It's a very rapid change in velocity, a big acceleration, big force required. It broke the balloon. Does the velocity get to 0? The velocity gets to 0 at some point at the bottom of the dent, at its deepest drilling into the surface. Suppose the first time I threw the balloon and it survived, it came to rest momentarily at the moment of deepest denting. So if you go throw your backpack, nothing fragile, on your bed, watch the bounce. When it lands, it will go right through what I call the equilibrium point, the point where it's perfectly supported. It'll go right past that and go extra deep. And it's at the bottom of that extra deep penetration into the bed, deepest dent. That's the moment of 0 velocity, when it comes momentarily to rest. And then it overshoots. And that bouncing motion, we'll do the bouncing motion in more detail soon. But bouncing motions, you go out on the Ruffner Bridge and bounce up and down. They got some fascinating characters to them. You hit motionless at the bottom and top of the bounce. At the bottom, you stop heading downward and begin to head upward. That's motionless. At the top, you stop heading upward and begin to head downward. That's motionless. So you reach no motion at the top and bottom. You're actually traveling fastest right through the middle, through that equilibrium moment. That's when you're swooping through up and down. And so velocity is 0 at the top and bottom. Acceleration is completely out of sync with that. The acceleration is strongest at the top and bottom and 0 in the middle. If that didn't make any sense, don't worry, we'll come back to it. But so we're almost at ramps, but I'm building my way up to ramps, and we'll continue it on Friday.